Hi, my name's Erin Clark.
I'm Ben Weaver.
And I'm Morgan Harlan.
And this is Lab 3, Gaussian Beam Imaging Systems. So in this lab, we examined the properties of Gaussian beam expansion, collimation, deviation, all along an optical rail. The general setup that we have of our beam is it's going through our microscope, which is essentially like condensing it down to a point at which we have our spatial filter, which is a pinhole we chose to be 25 microns, I believe. And then our beam is expanding out here, and then this 250 millimeter positive lens is collimating our beam, and then we have our blade setup, which we measured the profile of the beam at 2 different points beyond its converging point over here. This is a much nicer schematic of our system.
The first step of our lab was to align our spatial filter to the laser beam. So we decided to go with a 0.25 NA microscope objective and a 25 micron pinhole. And in order to align the spatial filter, we started by looking at the output of the pinhole and seeing when we could see the most amount of laser light coming through it. And then once we got a lot of laser light, we moved to holding a piece of paper out front in order to see the beam. And then we did adjustments in the X, Y, and Z directions in order to find the best aligned location of the pinhole when we saw the biggest spot without a lot of diffraction on the edges.
So as we moved the translation stage back and forth, we discovered that this shear plate had a greater sensitivity as the fringes moved with more with the lesser distance.
So one of the things that we wanted to ensure in this lab is the power differential that we're getting. So we use a photodiode that was set right next to the laser to see the input power, and then on the opposite side we're also using it to find the power and compare those readings. So when the beam is collimated, however, the spot is actually larger than the size of the detector. So what we need to do is actually defocus the lens such that we can get everything on the detector. Right here we actually have all the rays, ideally, in an ideal case, not everything is getting there because of some reflection. Everything is making it to the detector, and we have an accurate power reading, and we can compare those two values.
In order to complete our beam expander, we had to collimate our lens. So how we did that was just estimate the approximate focal length and then put at that point, and then we were able to see on the shearing interferometer where our beam is collimated by when we get horizontal fringes.
So unfortunately, we didn't realize this until after we had completed the setup, but our laser mount was a little bit unsecure. So in order to combat this and get accurate measurements, we had to take the air out of the table. Otherwise, whenever one of us touched the table, the laser beam would go off, sort of off axis like this, and our data readings for the power would change.
So to calculate the beam waste after our final lens, we did the same method as we did in the previous week. So using the knife scanning method, we found the two beam waste or two beam radii that was before and after the beam waste, found to be these values: 2,250 microns and 825 microns, and a separation between those 2 points of 91 millimeters. Then we used the algorithm, same as we did last week, so we won't go into detail of that, put it through MATLAB, and finally we found that our final beam waste was 5.961 microns, and that our final Rayleigh range was 1.764 times 10 to the negative 4 meters. And then to double check that we got the right root, or the right Rayleigh range, we plugged the values back in, and we arrived at the conclusion that delta Z is verified from our start.
Next, we were able to calculate the theoretical beam waste. We started by using the beam expansion ratio to find an intermediate beam waste, and then we were able to use that number in this equation down here to find the final beam waste, which we calculated to be 6.14 microns compared to our measured beam waste to be 5.961 microns. This gives us only a 3.4% error.